Hello again, physicists. Today's video, we are introducing something called mechanical work. This will be the first topic of our unit on work and energy. So to begin, what is work? It is a scalar quantity. And to remind you, what does scalar quantity mean? It means that this particular quantity will only have magnitude and that there is no direction associated with it. So when we talk about mechanical work being completed, we can only give it with a number and a unit. We really can't specify whether that work is up, down, left or right, positive or negative, east or west, north or south. So the equation for finding mechanical work is as follows. So we have W, which is work, being equal to F times D times the cosine of theta, where F is the magnitude of a force that's acting on an object, D is the displacement of that object or system, and then theta is the angle between the directions of the force and the displacement. Before we go any further, we should probably do a dimensional analysis to check out what the units on work will be. So the units of work will be equal to whatever the units of force times the units of displacement give me. So that means we will have the units of force plugged in for F, that would be newtons, times the unit of displacement, which is the meter, and then theta is just an angle, which is unitless. So we have nothing really to plug in for the units when it comes to cosine of theta. So this tells us that the units of work will be equal to newtons times meters, referred to as a Newton meter, and we actually have a name for that. We call that a joule, spelled like you can see right there. And we represent a joule with a capital J. So we measure work in joules in physics, or Newton meters. If you hear either or, they are both units of work. Okay, so I'm going to show you 4 different examples with varying forces and displacements and how they can line up and how that affects what the work would be from one scenario to the next. So in my first example, I am lifting a book. So with my hand, I am applying a force to a textbook and I am lifting that book up like so. So to find the work done by me lifting that book, I would have to take the force that is doing this work, which would be the applied force from my hand, and that'll be multiplied by the displacement of the book, and that will be multiplied by the cosine of the angle between the applied force and the displacement. Now in this case, the two forces are parallel to one another. This means that they are making a 0-degree angle between them. So the work done by this applied force will be the applied force times the displacement times the cosine of 0 degrees. And maybe from math class you remember that the cosine of 0 degrees gives you 1. So the work done by this applied force will be the applied force times the displacement times 1, which basically leaves me with what I have right here. And that means that this is positive work. Whatever you get from the cosine of theta, that will indicate whether it's positive or negative work. Okay, so for my second example, instead of lifting the book, I'm going to lower it. So now I'm going to find the work done by my applied force if the book is being lowered versus being raised. And you can see that my displacement is now in the opposite direction of my applied force. So to calculate the work, it's the same equation, but now what will be different is that theta is no longer 0 degrees. These are actually now separated by 180 degrees. So my work in example 2 will be the applied force times the displacement times the cosine of 180 degrees. Okay? And remember, we are not using direction when it comes to the force or the displacement. It is only the cosine of the angle that will give us directional information in any way, shape, or form. So that means that we're going to have the applied force times the displacement, and the cosine of 180 degrees would be -1. So this entire thing is multiplied by a -1. So I'm going to put a negative sign in front of here to show that. And that means that in this case, my applied force actually did negative work. All right, well, in my next example, I'm going to find the work that is being done by something besides my applied force. Because the truth is, there's also a force of gravity acting on this book, which I've illustrated in my picture. So, example 3 will be just like example 2. I'm lowering the book. But now we're going to look at what is the work being completed by the force of gravity instead of the work being completed by the force that I'm applying to the book. So we're going to use the same equation, only now I'm talking about the work done by the force due to gravity. And that means my force will be the force due to gravity times the displacement of the book times the cosine of the angle between those two things. So the cosine of theta is going to be 0 degrees again, because now the force that is doing the work is parallel to the displacement of the object. And that means that the work done by the force due to gravity here is going to be right there, Fg times d. And this is going to be positive work. So in the same situation, lowering that book, my applied force did negative work while my gravitational force did positive work, all because of the direction that the applied force and gravitational forces were pointing in and how that lined up with the displacement of the book. All right, so here's our last example where I'm holding the book, and instead of lifting it up or lowering it down, I'm moving across the room while holding that book to the left or to the right. So let's figure out how much work is being done by my applied force in this case. It's going to be the same equation that I've used in the past examples. We're going back to talking about the applied force here, not the force of gravity. And my angle between my applied force and my displacement, you may notice, is a 90-degree angle. So I'm going to do the cosine of 90 degrees now. And you may recall that the cosine of 90 is actually 0. So my work will be my applied force times my displacement times 0. In other words, in this case, I am doing 0 work. My applied force is doing 0 work on that book as I walk around the room. So make sure you get the notes down for all the different examples. Make sure that you include the illustrations that I've given, because it's very important to understand what this angle is. Because when we look at some problems, we may have an incline, and we're going to be asking about how much work is being done by different forces. And you got to understand that the theta in here is not the same as the angle of that incline. In fact, we're going to spend a decent amount of class time doing some simulated examples where you will have to make the distinguishment between this angle in my work formula and the angle that may be used to find a force while something is sliding up or down an incline. So with that said, until next time, physicists, until next time.